Imagine a place where time stops, light disappears, and the laws of physics crumble. Welcome to the world of black holes. These enigmatic entities, these singularities in spacetime, are where all that we understand about physics breaks down. They are cosmic curiosities that defy our comprehension, yet their existence is as real as the stars in the night sky. Black holes are the ultimate cosmic vacuum cleaners, sucking in anything that ventures too close. And when we say anything, we mean anything. From cosmic dust to massive stars, even light itself. The gravitational pull of a black hole is so immensely powerful that once inside, there's no coming back. This makes them invisible to our eyes and to our telescopes, thus earning them their name, black holes. But what exactly is a black hole? Imagine all the mass of a star, many times bigger than our sun, compressed into an infinitesimally small point. That's a black hole. A point in the fabric of space-time where gravity is so intense that it creates a well from which nothing can escape. This well distorts space-time around it, bending light and slowing down time. Yet, despite their invisibility, black holes are not entirely hidden from us. They reveal themselves through their effects on their surroundings. When they feast on nearby stars, they create a cosmic light show that we can detect from Earth. They also send ripples through the fabric of space-time, gravitational waves that we have only recently learned to detect. Black holes are the ultimate enigma. They challenge our understanding of the universe, pushing the limits of our knowledge and forcing us to rethink our theories. They represent the unknown, the unobservable, the unreachable. They are a testament to the vastness and complexity of the universe, reminding us of the many mysteries that still await our discovery. Black holes, the cosmic vacuum cleaners, are truly the universe's most mysterious objects. They are the ultimate expression of the cosmos's ability to astound, perplex, and intrigue us. They are a cosmic riddle, waiting to be solved. Stars, in their death throes, give birth to these enigmatic entities known as stellar black holes. The journey begins when a star, typically more than 20 times the mass of our sun, starts to exhaust its nuclear fuel. This fuel, primarily hydrogen, is what keeps the star burning bright and maintains its equilibrium against the inward pull of gravity. As the star burns through its fuel, it undergoes different phases. From a fiery hydrogen-burning main-sequence star, it transforms into a red giant, expanding its outer layers as it switches to helium for fuel. The star then shrinks into a white dwarf, having exhausted most of its nuclear fuel, but the story doesn't end there for some stars. If the star's mass is large enough, it enters a phase where it becomes a neutron star. The pressure of neutrons against each other is the only thing preventing the star from collapsing under its own immense gravitational pull. Yet, in some cases, even this pressure is not enough. The star implodes, its core collapsing inward while the outer layers explode in a brilliant flash of light and energy known as a supernova. This implosion increases the gravity of the core exponentially, pulling everything into an incredibly dense point. This point, known as a singularity, is where the magic happens. The gravity at the singularity is so immense that it warps the fabric of space-time around it, creating a region from which nothing can escape, not even light. This is what we call a black hole. So while it may seem like a tragic end, the death of a massive star is also a birth. The remnants of the star's core become a stellar black hole, a point of infinite density and gravity. The star's life may be over, but its legacy lives on, forever imprinted in the fabric of the cosmos. Thus, in a spectacular cosmic drama, a star breathes its last, leaving behind a stellar black hole. Lurking at the heart of galaxies, supermassive black holes dominate their cosmic neighborhoods. These celestial titans are not your average black holes. They are colossal, with masses ranging from millions to billions of times that of our sun, making them the galactic behemoths of the universe. How did these gargantuan entities come to be? Well, that's a question that continues to baffle scientists. One theory suggests that supermassive black holes are the result of the merger of several smaller black holes over time. Imagine a cosmic dance, where black holes, drawn together by gravity, merge to form larger and larger entities, growing in strength and size with each union. Yet another theory proposes a different origin story. This hypothesis postulates that supermassive black holes might have originated from enormous gas clouds that collapsed under their own gravity early in the universe's history. These gas clouds, having masses far greater than any star, could have given birth to the supermassive black holes we see today. Each theory offers tantalizing possibilities and raises more questions than answers. But regardless of how they formed, one fact remains clear. Supermassive black holes play a crucial role in shaping the universe around them. They're the central gravitational anchor of their galaxies, around which stars swirl in a cosmic ballet. The mysteries surrounding these galactic behemoths are many. How do they grow so massive? How do they influence the galaxies they inhabit? And what happens when they eventually consume all the matter within their reach? These are some of the enigmas that scientists are striving to unravel. But for all their mystery and might, supermassive black holes are not invincible. Even they, like everything in this universe, are subject to the laws of physics. And it's through these laws that we hope to uncover more about these celestial giants. As the kings of their celestial kingdoms, supermassive black holes continue to puzzle scientists. But with every new discovery, we inch closer to understanding these extraordinary entities in our vast and wondrous universe. In the first fractions of a second after the Big Bang, the universe may have birthed the most elusive of all black holes, the primordial black holes. Isn't that a tantalizing thought? These theoretical entities are a testament to the universe's potential for mystery and surprise. Primordial black holes, if they exist, would have formed not from the death of a star, but from the birth of the universe itself. As the cosmos sprang into existence, it was not a uniform soup of particles. There were minute variations in density, tiny pockets where matter was slightly more concentrated. Now picture this. In those moments, the universe was expanding rapidly, a period we call cosmic inflation. But in those denser pockets, gravity was trying to pull everything back. It was an epic tug-of-war on a cosmic scale. And in some rare places, gravity won. The result? A black hole. But not just any black hole, a primordial one. Unlike their stellar or supermassive cousins, primordial black holes could be any size. Some might be as massive as a star, while others could be as small as an atom, yet weigh as much as a mountain. Their size and mass would depend solely on the density of the pocket from which they formed. But here's the catch. Despite their fascinating nature, we have yet to confirm the existence of primordial black holes. We have no direct observation, no unambiguous signal pointing to their presence. They remain a beautiful theory, an idea that fits well with our understanding of the early universe, but lacks empirical evidence. Yet, the search continues. Because if we do find them, primordial black holes could offer an unprecedented glimpse into the universe's infancy. They could be remnants of the cosmos's earliest moments, frozen in time, waiting for us to uncover their secrets. While unconfirmed, primordial black holes could hold the keys to understanding the universe's earliest moments. And isn't that the beauty of studying the cosmos? Every discovery, every revelation brings us one step closer to understanding our place in this vast, mysterious universe. At the heart of a black hole lies a point where space-time curves infinitely, the singularity. This is the point of no return, where our understanding of the universe and the laws that govern it break down. The singularity is where the mass of a black hole is concentrated, a place so dense it's essentially a point with no dimensions. Imagine taking all the mass of our sun and compacting it into a space smaller than the head of a pin. That's the kind of density we're talking about. Our understanding of the singularity is clouded by the fact that it is a place where two of the greatest theories in physics clash head-on. On one hand, we have general relativity, the brainchild of Albert Einstein, which beautifully explains how massive objects curve space-time, creating what we experience as gravity. It predicts the existence of singularities and has so far passed every experimental test with flying colors. But then there's quantum mechanics, the theory that describes the behavior of particles at the smallest scales. Quantum mechanics is incredibly accurate in its domain, but it fundamentally contradicts general relativity. It refuses the notion of a singularity, arguing that it's impossible to squeeze matter into an infinitely small point. This clash of titans, this conflict between general relativity and quantum mechanics, is one of the most significant conundrums in theoretical physics. It's a puzzle that has given birth to new theories, like string theory and quantum gravity, in an attempt to reconcile these two giants. But until we can unite these theories, the heart of a black hole remains a mystery, a place where our understanding of the universe breaks down. It's a stark reminder of how much we have yet to learn, a cosmic enigma that continues to challenge our perceptions of reality. The singularity, a place of infinite density, remains one of the greatest enigmas in cosmology. As we continue our journey into the unknown, Let's delve into the event horizon, the point of no return when approaching a black hole. Crossing the event horizon of a black hole is a one-way journey, a plunge into the unknown. This invisible boundary, often referred to as the point of no return, marks the outer edge of a black hole. Its name, event horizon, paints a vivid picture of its nature. Beyond this point, no events can be observed from the outside universe. The event horizon is not a physical surface that you could touch or bounce off. Instead, it is a mathematical line in the sand, a point where the black hole's gravitational pull becomes so strong that not even light, the fastest thing in the universe, can escape. It's like a cosmic trapdoor from which nothing, absolutely nothing, can claw its way back. What makes the event horizon truly fascinating is how it affects our perception of time. For an external observer, time appears to stop at the event horizon. This means that if you were to watch something fall into a black hole, it would appear to slow down as it approached the event horizon, becoming increasingly redshifted until it finally faded away. From your perspective, the object would seem to hang at the event horizon forever, trapped in a perpetual state of falling. However, from the perspective of the object falling in, time would continue as normal. It would pass through the event horizon without any dramatic fanfare, without even noticing it. But once across, there's no turning back. The object is now at the mercy of the black hole's immense gravity, inexorably drawn towards the singularity at the core. So, if you were to find yourself on a one-way trip into a black hole, the event horizon would be your final farewell to the universe you once knew. Beyond it lies a realm of spacetime so warped, so distorted that our current understanding of physics cannot fully describe what happens. The event horizon, a boundary in spacetime, is the last sight that any object falling into a black hole would see. A chilling reminder of the enigmatic and unforgiving nature of these cosmic entities we call black holes. As matter spirals into a black hole, it forms a glowing halo of doom, the accretion disk. This cosmic carousel is not only a mesmerizing sight, but also a testament to the black hole's insatiable hunger. But how does this radiant circlet come into existence? Well, when a black hole's gravitational pull lures in nearby matter, such as gas from a neighboring star, the matter doesn't tumble straight into the black hole. Instead, it twirls around, much like water spiraling down a drain. This is due to a principle known as the conservation of angular momentum. As the matter whirls closer to the black hole, it speeds up and spreads out into a disk. This is the birth of an accretion disk. Now let's talk about the properties of these cosmic disks. They are astoundingly hot, with temperatures reaching millions of degrees. Why so hot, you might ask? Well, the matter in the disk rubs together as it spirals inward, creating an enormous amount of friction and consequently heat. This heat, in turn, causes the matter in the disk to glow brightly. And that glow is not just any ordinary glow. The accretion disk emits intense radiation, especially X-rays. From our vantage point here on Earth, we can't see a black hole directly. They are, after all, black against the blackness of space. But we can detect the radiation from their accretion disks. Observatories equipped with X-ray telescopes can catch this radiation, providing us with indirect evidence of a black hole's existence. So while the black hole itself remains shrouded in mystery, its accretion disk gives away its presence. It's like a cosmic lighthouse, signaling the presence of a black hole even across the vast distances of space. The accretion disk, a fiery testament to a black hole's insatiable hunger, is our best evidence for these invisible entities.